on Denver. I recognise that. Well, thank you very much. It's a great honour to be here. My task today is to describe to you something about the brain, its function and its potential. It's going to be very difficult, really, because the more I've learnt about the brain, in fact, the more I realise I don't know that much about it. It is really the unexplored territory of the body. It's a huge wealth of potential that we really haven't tapped into yet. And again, having done neurosurgery for many, many years, I can simply say to you that the more I learn about it, the more I realise I don't know about it. But I thought I'd stimulate you today, hopefully, with just a brief window into neurosurgery, what I've learnt from the brain, and some basic principles about the brain and how it is this huge sea of untapped energy. So it's a great unknown, really. The thing that attracted me most to it was that neurosurgery is a very young specialty, and in fact, we really don't know so much about the brain, and it's just a tip of the iceberg. For example, the brain sits in it's about 1.5 kilograms in weight. It sits in a fixed cavity, the skull, but it swims in crystal clear fluid called cerebrospinal fluid. And this cerebrospinal fluid phenomena is one that can kill you if you have excessive amounts of it. And if you don't have normal circulation of this fluid, then of course you can be left with terrible retardation, both psychomotor retardation and like I say, eventually death. But we still don't know the actual mechanism of its production, nor do we know the reason why we have cerebrospinal fluid. The brain sits in this pool of water. And one would think that it offers some sort of protection to the brain, but it hasn't even been proven to do that. The woody woodpecker picture is to basically tell you that if it did offer protection, one would expect a woody woodpecker to have heaps of CSF to protect his brain, but in fact there's no CSF in the woodpecker's brain or around the brain. So it's not just a protective phenomena. It doesn't just take away metabolites or take nutrients to the brain. And you would think that something as simple as CSF physiology would be understood by us, but it's not. It's just an example of how much we don't know. Neurosurgery is a specialty that appealed to me because it really started in the early 1900s. The fathers of neurosurgery were these two gentlemen, Walter Dandy on your right and Harvey Cushing on your left. They were both neurosurgeons from Johns Hopkins, and really the discipline of neurosurgery had its genesis at that university with these two great men. Yet, if they are the forefathers of neurosurgery, there's Walter Dandy on the right with his daughter Mary Ellen, and that's me meeting Mary Ellen in Portland, Oregon just a few years ago. So in many ways, the neurosurgeons of today still are second or third generation neurosurgeons when it comes to this particular subspecialty. So we're going to talk medical today, so I thought I'd give you a crash course on medical terminology. I want you to all read this slide and memorize some of those terms and sort of get used to using this medical term. Rectum, damn near killed him. I like that one. Okay, so excuse me if it's a little bit gory and a little bit highfalutin and technological, but I'll try and make it as simple as I can. The brain is, like I say, an organ that it is a bit mushy, like Susan said. It sits in a fixed container, the skull, floating in CSF. It really is a computer for the body, and if it is a computer, the neurons are the software, and the connective tissue, or the dendrites and axons, are the hardware. It is 2% of the total body weight, but it consumes a huge amount of oxygen and glucose and requires about 20% of the total cardiac output. This is a video of me exploring the inner sanctum of the brain, the ventricles. The ventricles that contain CSF or cerebrospinal fluid, and that's where it's produced. And again, one can see that in fact one can explore these ventricles and take out pathology that's in there and treat conditions such as obstruction of the cerebrospinal fluid with miniature cameras. So how does the brain work? Well, it consists of billions of nerves that all communicate with each other by chemical and electrical means. It's often said that you only use about 10% of your brain, and we don't really know where that figure came from, but certainly it probably arose from the fact that there are parts of the brain that we consider eloquent, that are absolutely vital to the way you think and life itself. And there are parts of the brain that are non-eloquent that you can just lop out with surgery. And believe it or not, the patients can be left functionally exactly the same, despite taking out very large amounts of this brain tissue. It receives messages from the peripheral nervous system, and then it relays those, it coordinates those messages in certain parts of the brain and then relays them out to voluntary function. Again, through the same nerves from which it gets the input. Susan touched on this, and it's a very important fact that even though the brain has a finite number of neurons and I guess hardware, there is a huge potential for those neurons to communicate with each other and in many different permutations and combinations. It's a very finely balanced relay station. It needs a huge amount of oxygen and glucose, and unfortunately is therefore extremely susceptible to any condition that limits the amount of blood supply to the brain and or oxygen or glucose. Well, does it work? Does it work well, I guess, should be the question. The answer is, well, there are some parts of the brain that are incredibly efficient, and believe it or not, there are some parts of the brain that could have been designed a whole lot better. The visual system, for example, is extremely inefficient. Those of you who know a little bit about the eye will know that, in fact, the visual input has to go through not only clear fluid, the vitreous and the aqueous humor, but it then has to go through a whole six separate layers of neurons and cones and interconnections before it actually gets to the retina where it's received. It's an incredibly inefficient system, and they say that, in fact, if the visual system was as efficient as the auditory system, you'll be able to see a mouse on the moon. So let's talk about the auditory system for a little while. I'm incredibly impressed by the auditory system. We know through studies that fetuses actually respond to sounds and vibrations long before they respond to any other sensory input. And we also know that at death, although the inner ear cells immediately die, the inner ear continues to transmit electrical impulses to the brain for hours after death. So the auditory system is, in fact, incredibly inefficient. It's the first to work and the last to stop working, and will even continue working when the host has died. The inner ear is composed of nerve cells from the ear to the brain that have individual fibers that perfectly transmit frequencies from inaudible, meaning you don't hear these noises, to the hearing range. Now that is incredibly fascinating to me because it means that we are picking up and transmitting sounds that we can't hear. And it's so fascinating, in fact, that some people have proposed that this is a possible explanation for people's sixth sense, or their ability to see before it happens. That phenomenon of déjà vu, of course, is a true pathophysiological phenomena. But in fact, even if you don't have seizures or temporal lobe seizures creating déjà vu, some people have this innate sense of being able to predict what's about to happen. And it could be, in fact, some mechanism by which the inner ear picks up vibrations and senses inaudible input. I'm not going to give you too much of a didactic anatomy lesson of the brain. It's a little bit dry, but in essence, the brain is divided up into many different lobes. The frontal lobe is the largest of all the lobes, and it really controls motor function, voluntary motor function, and some involuntary motor function. The back part of the frontal lobe is the primary motor cortex, and then that's separated from the parietal lobe, which is your sensory part of the brain that really interprets all the sensory input from all the different senses, not only touch, but also smell, sight, hearing, taste, etc. The occipital lobe is the visual part of the brain. It sits at the back. The temporal lobe is really a little bit unknown. We believe it has something to do with the downlaying of memory. It certainly has something to do with vision. but it contains a very primitive part of the brain as well. It contains part of the limbic system, and we'll talk about that in a minute. The olfactory bulb or olfactory area transmits directly to the limbic system. Again, an extremely primitive part of the brain, and that's why we believe that smells can bring back enormous amounts of memory because they connect directly to the memory areas. The cerebellum is this part of the brain at the back here, and it is basically a relay station that coordinates motor function. If you look at the inside of the brain, it becomes even more fascinating. And I think the thing that I find most fascinating is the fact that some parts of the brain are incredibly eloquent and sensitive. Unfortunately, there are still pathologies in those parts of the brain that we have to operate on and deal with. And you can imagine surgery in those parts of the brain are a whole lot more risky than other parts that are not so eloquent. For example, the frontal lobe, we believe is not so eloquent, but I guess that is a euphemism for meaning we really don't know what it does. But there are parts of the brain, such as the hypothalamus, which really do fascinate me and fascinate most neuroscientists. It's a small part of the brain right here. It weighs about 0.5 gram. It occupies less than 1% of the total brain mass. And yet it is the main executive of all autonomic or involuntary functions. It controls everything that keeps you alive and keeps you surviving, like memory, satiety, thirst, temperature control, pulse, blood pressure. Oh my goodness, it's just incredibly eloquent, and unfortunately there are conditions that affect primarily the hypothalamus. So you can imagine when that is affected, the whole being becomes extremely dysfunctional. It is also connected, well, it's part of the limbic system, again, this very primitive part of the brain, and I'll demonstrate to you how primitive and how important that is with some case studies later on in the talk. The ventricles are these fluid-filled cavities that sit within the brain. There are 4 different ventricles, 2 lateral, 1/3 and 1/4, and they all communicate. Unfortunately, again, the production and absorption of fluid is not well understood, and if it was, we'd be able to treat this condition called hydrocephalus, but unfortunately, about 1% of all patients with hydrocephalus will die every year without us really understanding the true mechanism of CSF production and CSF dynamics. So I guess I wanted to talk about the brain and its potential, given the topic of this conference, the mind and its potential. Again, as a scientist, I look for reasons why we are who we are, and hopefully we'll find a scientific reason as to why we function the way we do. I'm sure the spiritual part of me is in constant conflict with the scientific part of me, because I just wonder if in fact the mind or its mechanisms can completely explain all that we are as an advanced individual. So I'd like to talk about brain capacity, the limbic system, the ability to modify behaviour, and the power of the mind, and how all these topics have fascinated me with my exposure to neurosurgical conditions over the last 30 years. So this is the brain MRI scan of an individual who was 16 years old with severe psychomotor retardation. He was bedbound, essentially vegetative. He could communicate with grunts, but essentially he had to be fed and cared for. What fascinated me really was to see his brain looked essentially normal. The ventricles here, the fluid-filled cavities in the middle of the brain, are slightly enlarged, but essentially this is an MRI scan of a normal individual. This, on the other hand, shows incredibly big ventricles. By volume, these are probably 10 times larger than these ventricles, and you can see that the brain is suffering and that the thickness of the brain is significantly thinner than a normal brain. And yet this is a brain scan of an obstetrician gynecologist from a major teaching hospital here in Sydney. So I'm not going to mention his name, but no, he's very functional, a very intelligent man, and a great doctor, who I had the fortune of looking after, and I treated him for his hydrocephalus. But again, it fascinated me that he could function as a obstetrician gynecologist with a brain that looked so severe in its degree of hydrocephalus and the brain matter itself so compromised. Now, I could imagine this in a lawyer or a politician, but as a medical practitioner, really, I found it quite fascinating. What about the eloquence of the brain? This is a small cyst here in the brain stem. And again, the brain stem is a structure that's no bigger than the size of your thumb. It communicates the brain proper with the spinal cord, and all voluntary function has to go through the brain stem. And a lot of involuntary functions are also determined by structures within the brain stem. So a small cyst like this, which really only measures about 1 centimetre by half a centimetre, can create absolute havoc in the individual. And this patient, for example, was hemiplegic or paralysed down one side of the body with severe sensory symptoms down the other side of the body. Yet, on the other hand, this is the MRI scan of a young boy who was brought to me at 5 years of age asking whether I should treat this. But when I examined him, he was completely normal. He had no symptoms, and yet you can see clearly that this cyst is 100 times bigger than this cyst, and yet he is a normal young lad. This is the magnified image of the pituitary gland, which is also part of the central nervous system. It secretes hormones that are important to, again, our well-being and basically our existence. It's a coronal image, so you can't see the eyes, but basically it's a slice like this where the eyes are here and here. These are the ventricles, this is the brain proper, and this is the pituitary gland, this wide area here. You can see the tumour is only a small tumour here, about 3 millimetres in diameter, yet it has terrible consequences. This is the young girl in whom that tumour resides, and within 6 to 12 months of this picture, these people have actually consented to their images being shown. So, within 6 months of that picture, she then we have a frozen situation. Just hang on 2 seconds. She looked like that. So a huge effect on this girl, yet such a small tumour. Unfortunately, she was seen by many different doctors at some very impressive institutions. She was told she had an eating disorder. She was told then she had depression. She was treated for depression, saw a gastroenterologist, again at a major teaching hospital. And for 18 months, she just got fatter and fatter, and no one made the diagnosis. Eventually, of course, they blamed her mother for her eating disorder, and they accused her of having Munchausen's by proxy, trying to gain attention through her by overfeeding her daughter. Thankfully, she eventually had an MRI scan, and it showed that lesion. And again, please turn away if you get a little bit sick by blood. But I'd just like to show off that we can now take out lesions like that in the brain with minimal invasion, minimal trauma to the patient, and end up with very good results. So this is a endoscopic transsphenoidal transnasal approach to the tumour. So it's through the nostril, and that's my ear, nose and throat colleague just taking away one of the parts of the nostril to give us better access to the brain. We then use an endoscope and go directly to the pituitary gland. The beauty of this operation, of course, is it avoids having to retract the brain or even touch the brain. So all those potential complications of brain surgery, such as seizures, blood clots, infection, are all obviated or precluded because of this approach. Once we're in the brain, I'll just hurry this along. We don't have much time. So once we're through the back of the nose, we get into a thing called the sphenoid sinus. This is the covering of the brain, the dura, and within the dura resides the pituitary gland. And as soon as we open the dura, and this is me burning it, you can see that the tumour starts exuding out. And that's part of the tumour, that fluid. And then this more fleshy grey stuff is also the tumour, and it can be removed under direct vision with very little fuss and really no pain to the patient. This is her about a year after, and you can see that she looks a little bit. Oh, thank you. She looks much better. Unfortunately, she hasn't dropped all the weight off, but she certainly looks better than she did preoperatively. Again, this I find absolutely fascinating. We've done a few of these cases now with gigantic tumours that affect both sides of the brain. They used to be called inoperable, and one of the dictums of neurosurgery was that if you had a tumour that affected both sides of the brain, then you really shouldn't be offering any treatment because they are often neurologically devastated after surgery and cannot make functional recoveries. I defied that rule, and I've operated on many patients with bilateral lesions who come in good neurological status, and I'm pleased to say that most of them, not all of them unfortunately, but most of them end up still neurologically very good. So this is a general practitioner from the eastern suburbs. Again, I won't mention his name, but he had this incredibly large tumour that affected both frontal lobes. It's this big white mass here and this sort of heterogeneous mass here. After surgery, there was a big hole in his brain, and one would expect that this is the prefrontal cortex. It is the frontal cortex. It goes all the way back to the thalamus and those deeper parts of the brain, and you would expect that someone like this would be left with severe neurological deficits. This is him after surgery. He's back at being a GP, and he's a GP of note, and he's functioning incredibly normally despite that big hole in his frontal lobes. It fascinates me also that I've seen MRI scans of autistic children and individuals, and as you know, about 10% of patients with autism have an amazing capacity to memorize things. They call them the idiot savants. They were sort of popularized in the movie about Rain Man, but they are actually, it's a true phenomena. This true phenomena allows people like Dustin Hoffman in the movie to memorize telephone books, and for this young chap here to see an image for no more than 5 seconds and then to paint the details or draw the details of that image over the next few hours with 100% accuracy. And yet their brains structurally are the same as your brain and my brain. So that to me tells me that the capacity of our brain must be enormous, and if we could only tap into that capacity, I think we could do amazing, amazing things. The limbic system also fascinates me. It's very primitive. Oh my goodness, I've only got 5 minutes, so I'll be very quick. But essentially, this is a young girl who had rage attacks, and so bad that she was almost institutionalized. She was stabbing her brother and her mother, and she was always angry. We did an MRI scan on it and found that she had this small lesion in the limbic system, the hypothalamus. The surgery was, again, minimally invasive endoscopic surgery where we shaved off some of that benign tumor, and again, because of time, I'll just go straight to the and this is her straight after surgery. You can imagine you couldn't even communicate with her beforehand. She was so angry. And essentially, this is her after surgery. She's telling us that she's not angry anymore, no longer having any violent attacks, and a very pleasant teenager, if there's such a thing. This is another case that fascinated me. We're running out of time, so I'm sorry, but it'll be very quick. But essentially, this is a 48-year-old lady that was brought to me when I was in Arkansas as a neurosurgeon. She had widely metastatic cancer of the breast. She was in terrible, intractable pain because of bony metastases. Her life expectancy was only 6 months, and they asked if I could do anything for her. There's an operation called Cingulotomy where you put a lesion in a part of the brain called the cingulum, also part of the limbic system. But at the time, they came out with these deep brain stimulators, and I thought that I might try a stimulator on this lady and put it in the cingulum just in case I got a complication. I could then change the electrodes of the deep brain stimulator. It was amazing that she woke up when we had the stimulator off and she had terrible, intractable pain. But when we turned the stimulator on, she experienced these strong feelings of sexual arousal with the pain. And she died 6 months later, or about 8 months later, but she died incredibly happy. And she had this almost desire to want the pain. I looked into it because it had never been documented before. And in fact, it has been in the literature that you can get sexual arousal from pain. And the mechanisms by which you get that are very complex, but nevertheless, suffice it to say that it has been studied, and there are direct and indirect pathways that go through the cingulum to the pain-receiving areas of the brain. Can pain be pleasurable, the bottom line was, and the answer is, well, it's a bit ironical, but But Susan looked at the Google and looked up honour. Well, I looked up Google and BDSM and found that there were thousands of websites on BDSM. So obviously some people find pain pleasurable, and it was also fascinating to hear that there are 1,000 hits per second on these websites. So the bottom line is, yes, pain can be pleasurable to a certain percent of the population, and that you can induce this sort of pleasure, and it's not just learned behaviour. I have to round up now, but the bottom line is you can modify behaviour by modifying certain parts of the brain. This last slide I think is absolutely fascinating. I'd just like to share it with you. 1 minute to go. This was a randomised double-blind study back in the 1990s looking at clopidogrel and aspirin. They're both blood thinners, and it was meant to be class 1 evidence. In other words, you need a double-blinded, placebo-controlled study. What that means is that you have 3 groups, 1 group on aspirin, 1 group on clopidogrel, and 1 group taking sugar tablets. And what you do is, and you give them the thing, and then you check their blood coagulation profile. And we found that at the end of the study, there was a reduction in the profile, blood clotting profile on patients with aspirin by 78%, and those on clopidogrel by 76%. But the most fascinating thing about the study was that those taking a sugar tablet could thin out their blood. Now, I find that incredibly fascinating. I can understand how you can use the power of the mind to overcome pain, to boost your immune system, but to be able to thin out your blood by thinking that you're taking a tablet to thin out your blood, to me, I find absolutely fascinating. How this happens, well, unfortunately, I don't know, and hopefully the good Dalai Lama will tell us tomorrow. Thank you very much.